Hello, welcome to my YouTube channel. So we'll continue from where we stopped. In this video, we'll expand on another concept. So this concept is also called the energy mass equivalence theory, proposed by Albert Einstein himself. So this theory was summarized in a very simple equation I'm sure you've all heard of. So we say E is equal to mc squared. So this simple formula is trying to show that to some degree mass and energy are the same thing. Let's get into the main content today. So we'll talk about work. So what does it mean when you talk about work? In the previous video we described what work was. So we said work refers to the transfer of energy that can be used to change the height of a weight somewhere in the environment. Yeah, that's how we think about work when we think about a thermodynamic process. Suppose we had a system. If that's the case, addition of heat to this system will do two things. We discussed that in the previous video. We said it will cause this system to gain in internal energy, and it can also cause this system to do work on the environment by moving the piston some distance x. So as you're able to see in the next diagram here, you're able to see that the piston has moved some distance x. So if that piston moves some distance x, we can try to quantify what's going on here. So if we wanted to express the first law of thermodynamics, we'd say an addition of heat is equal to we'd say the change in internal energy plus the work done. But then the question is, how much work will be done? How can we express the work done? So we can go back to our concepts of physics. We know that pressure is equal to the force per unit area, right? And then if we had to make force the subject of our formula, we'd say force will be equal to the product of pressure and area, right? Okay, let's skip that. So we also know that work is defined as the product of force and distance. And then for the sake of this problem, the distance displaced, we've used an x. So therefore work is also equal to force multiplied by x. So since we have an expression for force, we said force will be equal to the product of the pressure and the area. We could get pressure in area and then substitute it in that equation. Then we'll have work will be equal to the product of pressure, area, and the displacement x. However, multiplying the area and this displacement x, which is the height, gives you the volume. So therefore, work done is equal to the product of pressure and volume. In real practice, we do not get the absolute value of the volume. Instead, we are looking for the change. So it's V2 minus V1. Therefore, work done can also be calculated by multiplying the pressure by the change in volume. So this is a very important equation because it means we can substitute it in the first law of thermodynamics. Therefore, we'll say quantity of heat added to a system will be equal to the change in internal energy plus the product of the pressure and the change in the volume. Now, the next thing I want to talk about is the concept of maximum work. What's the highest amount of work that can be done by a system? So when we talk about maximum work depends on the external pressure. So if the pressure outside the system is significantly great, one thing you'll be able to see is that this system cannot do work on the environment. Instead, the environment will do work on the system. And then if the pressure of the environment significantly drops, then the system will be able to do work on the environment. Now, you need to know that in an isothermal process, we described what an isothermal process is. We said in this process, temperature is constant. In an isothermal process, the work done may be represented differently. The ideal gas equation allows us to say that PV is equal to nRT. If PV is equal to nRT, then we've established that the product of pressure and volume gives you work done. Therefore, work done should equal to the product of nRT, right? However, multiplying the number of moles, the gas constant, and temperature will not give you an exact value. Instead, there is a function of proportionality. You can think of it as a constant of proportionality that has been added to the equation. So we say the maximum work done in an isothermal process will be equal to the product of the number of moles multiplied by the gas constant, multiplied by the temperature, multiplied by the lean of the quotient of the volume. Work done can also be calculated by multiplying the pressure by the change in volume. What am I trying to say? In other words, in an isothermal process, you need to know that in an isothermal process, if you are to plot pressure against volume on a graph, right? If you are to get the area under that graph, you would get the maximum work that can be done by that system. The maximum work done will be equal to the integral of the product of the pressure and the volume. Yeah, so that's another thing that you need to take note of. So what other piece of information does this give you? So in an isothermal process, we know that temperature is kept constant. If temperature is kept constant, the change in internal energy is also equal to 0. Internal energy is not changing. If that's the case, then you can be able to tell, if that's the case, then you can be able to tell that the first law of thermodynamics can be expressed in a different way, right? So if we set internal energy equal to 0, then what we'll have is we'll say the quantity of heat added will be equal to the work done. Therefore, this expression of work done, where we said work done equals to nRT ln of V2 over V1, can give you two things. It can give you the maximum work and can also give you the maximum amount of heat added to the system. Another thing I could add is in an isothermal process. An isothermal process, we said we describe work, the maximum work, as being the negative of nRT multiplied by ln of V2 over V1. But Boyle's law tells us that for an ideal gas, the pressure and the volume are inversely proportional. It is also possible to express the equation for work in terms of pressure. So we could say the maximum work will be equal to the product of nRT ln multiplied by pressure 2 divided by pressure 1. So this is generally another form of the equation you see. That will be the last thing we discuss. Then the next thing we'll discuss after this will be thermochemistry. Yeah, so that will mark the end.